Okay, so here we have the first part of Lab 11. This part creates a slow speed oscillation using a programmable unijunction transistor. So this transistor right here, does not have the same function as the bipolar junction transistor we used in the previous lab. In this lab, this transistor kind of acts as a control gate. You've got an anode, a cathode, and a gate in the middle. The gate controls what can go through the anode and cathode, but it's not variable at all. So if there's enough current, the internal resistance at the gate drops low enough, all the current at the anode will push right through the cathode, which is the bottom pin in this case. So as you can see, we've got our 6-volt power supply. Already got the negative hooked up. We'll put the positive up when we're ready to see. We've got this top resistor right here is 470 kiloohms. This one right here is 15 kiloohms. And this one right here is 27 kiloohms. These two are attached from the positive to the anode and gate of the programmable unijunction transistor. Excuse me. Just trying to zoom in correctly. Yeah. Also attached to the anode of the programmable unijunction transistor is a 2.2 microfarad capacitor. This is directly hooked up to the negative. Attached to the other side of the gate of the programmable unijunction transistor, we have our 27 kiloohm resistor. I'm sorry, that does go to the gate too, yes. And it also goes directly to the positive. And attached to the cathode, we have a LED, which goes directly to negative. So, let's see what happens here. Just plug in the positive. Oops. Plug in the positive. Oh. The LED is flashing. It's kind of interesting. I wonder what's going on here. Well, if you think about it, I just unplugged this to save the batteries. If you think about it, we recall from Lab 9 that it takes, I believe it was Lab 9, yes, that it takes time for a capacitor to fill. So, if we just think about what's going on here, positive current is going through. It's going to the anode, but it's being blocked by the gate. However, this resistor, the top resistor, the 470 kiloohm resistor, is also going to that capacitor. It's a pretty high resistance resistor, so that takes the capacitor a bit of time to charge. The capacitor is a much lower capacitance than the one we used in Lab 9, but it still notably it gives it visible time to charge. So the capacitor is also directly hooked up to there. There's nothing interfering. So the capacitor can fill, and it goes to the negative, and it empties. Given that we have got the batteries over there. I'm sorry, that's not why it empties, but I'll explain why it empties in a moment. So we also have... Why does it empty? Oh yeah, because it's a capacitor, sorry. It empties because it's, touching. It empties because it's a capacitor. I'm sorry. The nature of capacitors, which I explained in Lab 9. This resistor is attached to the gate, so that's why. It's directly taking the current from the capacitor and emptying it because it's making a complete loop here. And it's also filling it too. And then attached to the cathode, so this resistor allows the internal resistance of that to become low enough that the current in the anode can go right through the cathode. However, this is also directly connected to the negative. So here's how it goes. The current is going to go through the top resistor, and it's going to open this, but the positive is opening the gate. So it can come through the anode and go to the cathode, and go to the LED, light up the LED, and then there's not enough current left over, because the capacitor is filling up. The capacitor is filling up and then returning the current back, hence why we're getting the flashing lights. And I believe... Yeah, the surge depletes the capacitor. The LED surge depletes the capacitor. So yes, that's the first part of this lab. We're going to expand on this when I come back. Okay, so now we've got more of the circuit. We have some more resistors. 470 kilo ohm, again, but one right below that's 33 kilo ohms. This one right here is 100 ohms, and this one right here is 27 kilo ohms. We've got a ceramic capacitor that's 47 nanofarads, 4.7 NF. That can be confusing. And another type of the 2N, what's it called? 2N6027 unijunction, programmable unijunction transistor. We also have an 8 ohm loudspeaker that is 3 inches. It's supposed to be 1 inch, but I don't have a 1 inch. Doesn't matter what the polarization is on it. Actually, it's kind of a nice feature of it. Same with that capacitor. Now here, this capacitor is a lot lower capacitance, so we do have to use a bit lower, different kind of resistors as well. 47 nanofarads compared to 2.2 microfarads. It's very much smaller. Ceramic disc capacitors tend to be that way. We've got the, I believe, the same resistor from the other side of the base to the other side of the gate to the negative is up here. The same going to the anode, except this time from the cathode we've got a resistor and a loudspeaker, because the light would be flashing too fast for us to see, because this capacitor is going to empty much faster. I have my information a little, I skewed the information a little bit. What's going on here is that the capacitor takes about 5 seconds. It takes roughly 5 seconds up here to get to 6 volts. But the unijunction transistor is connected directly to the capacitor, so when the voltage accumulates on the capacitor, it also accumulates on the transistor. So when it finally reaches the threshold, it flips the programmable unijunction transistor into its on state, because that's the threshold for which it has to break through, because the amount going into the anode matters how much the gate matters for how much it takes for the gate to change. So when it finally breaks the threshold, it puts the transistor into its on state, which lets it through. The capacitor immediately discharges itself too through the transistor, through the LED, which flashes, and from there goes to the negative side of the power supply. Sorry, I veered off a bit there. So here the same thing's happening, but it's going to take a much shorter time for that capacitor charge, and we won't be able to see that with our human eye. So that's why we're using the loudspeaker. Sound works in frequency, or hertz. So if we've got an electrical signal passing very, very quickly, many times a second, maybe we can get some sound out of that. Because we can't see something flashing that quickly. Our eyes in this camera is just not good enough to see that. But if we express it, if we show it differently, we use a different method of showing it, such as sound, we can definitely hear it, or see the effects of it. So I'm going to plug the positive in now. So you can still see that the LED is flashing. You may or may not be able to hear this. Very, very faint. If you can't, you're going to have to trust me on the fact that it's happening. It's very high-pitched and very quiet. However, in the next part of the lab, we're going to amplify that sound using another type of transistor. See you in a bit. So here, I've removed part of the circuit and changed it around. So on the cathode of this one, we now have a 1 kilo ohm resistor going to the base of a 2N2222 bipolar junction transistor. The collector is connected to one end of the speaker. The other end of the speaker is connected to our previous, resistor. Our previous 100 ohm resistor, which is connected to positive. That's going to the collector. The collector, yep. And then I'm sorry, just a moment. Yes, okay, I had that correct. And our emitter is connected to the negative. Our base is connected to this transistor, which is also connected to the emitter, to the cathode of the unijunction transistor. So it's oscillating very quickly. So the oscillations are going to the base of this one and controlling the current, and controlling the amount going through here at an oscillating pace. So it's going to be rapidly pulsing through this transistor. And as we know, this transistor you can use a small amount of current to to get a much larger amount, to control a much larger amount of current. So, if we do this correct, if this is done correctly, this means that there's more current going through there, so the oscillations have more current behind them, and this should be louder. So, I'm going to plug in the positive, and as we can hear, it's very loud and annoying. Very, very loud. It's still flashing. I'm going to turn that off because that sound is very, very annoying. It'd be even more annoying on a 1-inch speaker. You can amplify it some more, but for the sake of my ears and everyone else's ears, I'm not going to do that. You can use another one of these transistors in the same kind of method to amplify the sound even more, and you can keep going and going and going, increasing the voltage and stuff, and it gets deafening till that speaker can't do anymore. And that speaker, it's loud as it is, and I don't really want to kill my ears and everyone else's today, so I'm just gonna have to tell you to believe that it works. That's it for this lab. Thank you for watching. I'll see you next time.